All right, so for now, please stop clicking. Michael. So, like I said, we're going to go over a little bit of binary, a little bit of ASCII, and just how a computer takes in information, processes it, and then sends it out. So, this is the basic. I really wish I had a black marker. All right, I'll have one for tomorrow. So basically how a computer works, this is our computer. There we go. So what we do is we type in a language that we can read. We English or Spanish or whatever. We're using English in this class. So we type in, hello. A computer, all a computer can understand is ones and zeros, binary, right? It can do nothing else. It can understand nothing else. And computers only do what you tell them to. So if you're sitting there and your computer's going, no, my computer's not doing what I want it to. No, it's doing exactly what you told it to. What you're telling it to do is wrong, right? So don't ever, it's something I fight with that because I'm like, no, I'm right, the computer's wrong. But so we type in the words hello. A computer obviously can't understand that. Oh, that's much better. So everything, every button, every number, every key on your keyboard has an ASCII value, which is ASCII, and I can't remember what it stands for. If someone wants to look that up and let us know, that'd be awesome. What that means is every letter has a number associated with it, from 0 to 255. Which, just so you guys know, is 256 numbers, right? Because you have to include 0, then 1. And that is equal to 2 to the 8th power. Excuse me. That comes in handy in my networking class a lot. Yes, Michael?
American Standard Code for Information Interchange.
There we go. I won't ask you that ever again, what it stands for. It's just something that I wanted to know. So, but you can kind of ignore this. That's just whatever. So, H, E, L, L, O. Each one of those, like I said, has a specific number that's an ASCII value. There are capital, lowercase h does not equal uppercase h. Those are two distinct numbers. Excuse me. And again, I should probably memorize or at least have the table up. But we're going to come up with numbers. Oh, I think lowercase a, I think this is 96, and this is, 55 or whatever. The reason why smaller a is a bigger number is alphabetical order. A capital number, a capital letter is seen as more important and it comes first before a lowercase letter. Does that make sense? This ASCII value, knowing that how this works, is important when we get to if statements because you can actually code alphabetical order. So if Mark comes before Mary in the dictionary, say something. So you have to be able to evaluate those two things. So once the computer takes our hello and translates it to numbers. So then this gets turned into, again, I'm just going to make up numbers because I can't remember. 60, and then 105, 110, 110, and then 120. The computer sees these 5 numbers. What it then does is it takes these numbers and breaks them down into 8 bits, 8 byte numbers. So this gets turned into, that's 4 before 2 to this 0, 0, 1. Anyway, I'm just going to make up a number. It gets turned into that, and then 105 gets turned into another string of binary numbers, and then same with this. And once it gets here, your computer processor can determine what you're telling it to do. It's only when it gets into a bunch of binary code, excuse me, when it gets into binary that your computer can actually do something with it. Does that make sense? All right, you basically translate from human speech to really close to machine language into binary. So then this is 1 0 0 1 0 0 0 1, whatever. Then the computer does stuff. And then if you tell it to display information, what it then does is it then moves it back into ASCII and then back into vernacular. Does that overall process make sense? Right? You can kind of think of this as English to someone who speaks English, Spanish, and Chinese, and then into Chinese, and then back to the dude who speaks English, Spanish, and Chinese, back into English. Yes?
Is ASCII like the 60, 105?
Yeah, so, geez, I have no idea what's wrong with my throat. This is ASCII, this is binary.
So is that like the process of how like what we type gets on the screen?
No, this is what you type, because what we're doing is we're telling the computer to do things, right? We're telling it to compare these values, we're telling it to create a variable, we're telling it, hey, I need you to take this user's input, multiply it by a number, and then display that number. So we're telling the computer what to do, and in order to do that, in order for a machine to understand a human, you need a translator. That's what these two steps are. That's what this step is. This is a translation of human speech into machine speech. And so then we're telling the computer to add numbers together or to do whatever, and then to display that information, it has to go back into ASCII, back into something we understand. If you don't have it translate, you can look at, I don't know how, but anyone seen The Matrix? Right, that's your favorite movie, right? Yeah. Who has seen The Matrix? Raise your hand high. Oh, wow. Less than I thought. So basically there's this scene at the end when the character looks around and just sees code, right? If we don't have a translator, all we would see is code on our screen. Now I'm gonna see if I can look that up real fast because it's super interesting. I would love to watch the whole movie, but we can't. That would be super cool. Actually, that would be good for my intro to robotics class, maybe. Neo realizes he's the one. This is so for those of you who haven't seen it, long story short, this is a movie in which humanity is forced underground because of machines. And this is the climax of the movie. This is the very end. So spoiler alert, but it's also almost 20 years old at this point. So, and then she says, I love you. Oh, is this it? Here we go. So this is kind of what a computer understands, right? Imagine all these are ones and zeros. Obviously, we can't tell what's going on. We need the translator. He's the special one. He's kind of like the special. You guys seen the Lego movie? Have more people seen the Lego movie than Matrix? Yeah. It's kind of like he's the special one. He can understand it. So if we don't have this ASCII from binary in between human and machine language, we can't use computers. We would all have to learn binary and be able to understand it faster than you do English. So that's why this step is important. Okay, and so real quick, I will teach you briefly how binary works. What does the prefix bi stand for? 2. So in binary, there is 2 options. You have a 1 and a 0. So when people say the decision isn't binary, that means it's not a yes or a no. It's not black and white. There are gray areas. With binary, there are no gray areas. It's literally a yes or a no. And the reason why it's a binary is because the way a computer first started to work was it measures the flow of electrons through what are called logic gates. An electron through a gate is a 1, an electron not through a gate is a 0. So it's literally isn't one single electron going through a gate. And as you build logic gates, you know, yes, no, maybe, this and that, this nor that, as you build it, that's how you actually get an operating system. That's how you get the base of a computer. And then once you have the base of a computer, you can then build upon that. Zach.
Would computers get more advanced if there was like 3 numbers instead of 2?
So I don't think there is actually, I don't think a computer works in anything but binary. I know there's, I think it's tertiary. No, I don't think there's trinary. But what they're doing is that with supercomputing, they want to use quantum. It's called superposition. So you can have with one I think bit, which is 1 number, you can have 4 options. So at the amount of processing power we have, it's not that big of a difference. But if you have a supercomputer, it's, you know, squared times faster. Does that make sense? So as the bigger and more powerful of a computer you have, the bigger the difference between using binary and using superposition quantum computing. Now there are a lot of videos that can explain that a lot better, and that might be something we do tomorrow or even later today, depending on the time, that explain that sort of stuff I'll say way more entertainingly than me, because it's not just me talking. But so you have a 1 or a 0, and so you guys know what a byte is, right? B-Y-T-E, not like a bite of a sandwich. A byte is 8 bits. A bit is a 1 or a 0. So this is 1 bit. 2, 3, 4, 5, 6, 7, 8. This is 1 byte. Make sense? So this is something very important when you're shopping for download speeds in your home network, and they say 60 megabits per second. You're like, oh my gosh, I can download 100 megabyte file in a second and a half. It's not true. A bit, they're talking about 60 of these things, 60 individuals, and all of our storage is done in 8. So if we get 60 megabits per second, that equals 7.5 megabytes per second. Yeah, so at this speed, because this is what I get at my house, I can download a 100 meg file in, 15 seconds, 12 seconds. But you think, oh, I get 60, it should be a second and a half, and then you call and they're like, oh no, your service is totally fine, it's totally up to normal, it's totally at speed, must be something wrong on your end. Well, technically yes, because they don't. There is a legitimate reason why storage is done in megabytes and transmission speed is done in megabits. I can't remember it though. So that being said, if you only learn one useful thing today, that should be it. Because that's actually a real world application of stuff. So this is called an 8-bit number. You guys have heard of 8-bit graphics, right? Or 16-bit graphics. All those 80s video games that, like Pokemon. Did you guys play the original Pokemon? Damn, you guys are so young.
One of them is not like
So basically, 8-bit graphics means they use a base of only 8, and then we get 16-bit graphics. You can use 16, so you can store more information, make your characters look higher detail. So how does binary work? Works the exact same way as our decimal system. What numbers do we have? What numbers do we use? 0 through what? 0 through 9. How many numbers is that? Decimal. Pretty cool. So the way this works is if we have we start with 0, and then we add 1, and we have 1. And then 2, 3, 4, 5, 6, 7, 8, 9. When we get to 9, what happens? We add a 0 here and a 1 here. Then we get 10. Then what we do is we then start all over. We get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 6, 7, 8, 9. Then what happens? We get a 0, 2, or I'm sorry. Yeah, then we get a 2. And then we start all over again. Then we get 21, 22, 23, 24, 25. Then we get to 30. And then this number goes from 0 to 9. And every time it goes through 1, this increases by 1 until it gets to 9. So we follow this, and then we get to 99. What happens then? We have a 0, 0, carry the 1, and then we have 1, 0, 0. Then we start all over. 1, 0, 1, 1, 0, 2, 1, 0, 3. And that's how we count. Every time we get to 9, the next thing we do, it becomes a 0, and then we move, the next number changes. Right? That makes, you guys understand that's how decimal works, right? The same thing with binary, except instead of 10 numbers, it's 2. Now, I get this is boring, and I get this might not be, what is coding? Like, this is just something that I think you guys should know. It's in most computer programming, just basic how a computer works real quick. After today, I won't really bring up binary, right? This is just intro to you guys so you guys can understand, oh yeah, base 2, I know what that means, this, and it helps you understand computing better. So especially when you get to hexadecimal. You guys ever done like media arts and you pick a color and it's like hashtag FF0AB1? Yes, no, if you've never done Adobe Photoshop or anything like that, but every color has a number associated with it, with letters. That's the same thing as this, except it's using 16 as opposed to 10. So it's 0 through 9, A through F. And that's really important for IPv6 addresses, which again, a lot of it, I cover this a lot more in my computer networking class, but not enough people took it this year, so. All right, so binary, we're gonna come back over here.
I heard that one.
So we have 0, right? We're gonna start with 0. What's the next option we have? 1, right? So then we go to 1. Now we only have 2 options, so now what's gonna be our next letter? 0, and then what do we do? Move to 1. Then what's our next number going to be? And then what's this one? Okay. Then what's our next number going to be? Then what's this one? What's this one? Okay. You guys are killing it. What number do you think this is when you translate it from binary to decimal? 0. What's this one?
1, 2, 3, 4, 5, 6.
Correct. Wait. 6 in binary. No, this should be that. Right? So I screwed, one of those is wrong, I know that. I know this is right. So we're gonna keep that one. One, 2, 4, yeah, okay. So that's correct. So how binary works is this is all to the power of 2, just like, all right, so let's do 14,621. This number here is what place? You learned this in like first grade. It's the ones place. So 10 to the 0 is what? 1.
Oh, 0, 1.
Yeah, no, don't worry, I do that all the time. This is the what's place.
Yes.
So this is 10 to the what power, which equals and then 10 to the 2, 10 to the 3, 10 to the 4, which is 100, 1,000, and 10,000 respectively, right? Okay? What this means is we are doing 1 times 10 to the 0 is what? Actually, I'm going to start this the other way. I'm going to start biggest to smallest. So this is 1 times 10 to the 4th, which equals what?
No.
10,000. Then we have 4 times 10 to the 3, which equals what? 4,000. And then I have 6 times 10 to the 2, which equals
600.
Then I have 2 times 10 to the 1, which is, and then 1 times 10 to the 0 is. And then you add all those together, all those numbers up, you get 14,621, right? Same thing happens over here. This is going to be 2 to the what, do you think? 0. And then this is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7. Tracking with me? Yes, no, vaguely. Vaguely, okay. Again, this is, I know this is boring. This is just something every computer science, every book covers this if you start programming. It's like basic computers so you guys can understand how a computer thinks, okay? I think we have 15 minutes-ish. So, oh, I should have kept that up. All right, we're gonna figure out whatever number this is, right? So let's start from the biggest. We're gonna go 1 times 2 to the 7th equals what? Does anyone know what 2 to the 7th is?
70.
No. It's 2 times 2 times 2, 2 times 2 times 2 times 2 times 2 times 2 times 2, which is 128. Is 1 times 128, which equals what? And then we have 0 times 2 to the 6, 0 times 2 to the 5, 0 times 2 to the 4. And then we're at 1 times 2 to the 3, which equals 1 times what? 8, which equals 8. Then we have 0, 0, and then 1 times 2 to the 0 is what? 1 equals. So this number right here in binary is 137. That's how binary works. And if you ever see a binary number and it ends in a 0 or it ends in a 1, you automatically know it's going to be what type of number. An odd number, because you're always going to add 1 to it. So knowing the powers of 2, especially in computer networking, is like a requirement. You know, 1, 2, 4, 8, 16, 32, 64, 128, 256. Those are the most, knowing that off the top of your head is really good for computer networking. You guys have any questions? Is this at least somewhat interesting, how binary works? Like, it blows me away that we figured this out. That like in the 60s, people are like, oh, let's do binary. Well, that totally works. Logic gate. Yes, no. Everything is built on one of 2 options. Like that, everything in your phone, everything in your computer breaks down to a 1 or 0. That blows my mind. Right? And the fact that a computer can do it that quickly, I'm going to show you guys something real quick that every time I see it blows, I just think it's awesome. It's a GIF. You guys have, who here has ever heard of the video game Doom? Right? It's a first-person shooter where you're running around and you're shooting, I think, demons or something like that. So this is a GIF of the game being rendered. This is each step that the computer does to render one single frame of your game. Some computers can do that 60 times a second. That blows me away, especially if you're running around moving. This is just one frame. If it's keeping track of your bad guys moving at you, it's keeping track of how much ammo you have. It's doing all this stuff, and it does that 60 times a second. And it's all 1s and 0s. The color on your screen, the pixels, the individual pixels on my screen or the TV are being told what to do with 1s and 0s. 2 options, and everything is built off of that. Seriously, that's so cool. Anyway, so any questions, comments, concerns, suggestions? No. One thing I forgot to do, normally on block days, I do about 45 minutes and then a break. I totally forgot to do the break, and there's only about 10, I think, minutes left of class. I honestly have no idea how much left of class is.
I think it goes to 30 because then.
Then you have the break.
Oh, so I think it goes to like 24.
But then 7th hour is a full hour and a half of my class, isn't it? So I think it probably goes to 1:30.
I think it goes to 132.
And then you have a 6-minute passing period, and then you have one more class. If I had to guess, that's what it is. So you guys got 24 minutes. Let's all stand up and stretch.